the second method that we use to conduct the order of magnitude estimate is we use the cost capacity method. So what is that about? Let me give a short PowerPoint that is available on Canvas. So this is based on the study, the shorts provided at the bottom of the slide, you can see. And the study conducted throughout many wastewater treatment plant projects. And they want to determine the relationship between the cost and the capacity. So the just give you a brief overview. You are an expert, for those of you especially environmental engineering major. You are expert in these areas about the wastewater treatment. So they classify for this study 3 types of wastewater treatment. The first one is cluster. Typically for the capacity 10,000 gallons per day and serve 30 homes, so basically a very small subdivision. For the satellite wastewater treatment, it can capacity up to 100,000 gallons per day. It serves about 30 to 1,000 homes. So the last one, it's centralized. The capacity is more than 1 million gallons per day. Something if you have near our campus that have Three Oak wastewater treatment plant have 6-7 million gallons per day. So it's more centralized and it serves more than 10,000 homes. If you can see the cost, of course, if you buy a cluster, if you build a cluster wastewater treatment plant, it will be cheaper. But in terms of the capacity to build 1 million gallon per day capacity, we have to build hundreds of the cluster wastewater treatment plants. So it's the economy of scale, etc. It will affect the cost. So for that reason, we need to see the relationship between the cost and capacity. And what people found out here in this study, and they separate for 2 types of costs: construction costs. So basically the design, the engineering and construction to finish the project. And then the O&M stand for operation and maintenance cost. At the project in operation, how many dollar I will treat it for per gallon. And from this study, if we have a cluster for every gallon per day capacity, it need $108 of the design flow there. But for the 1 million gallon per day, you only need $19 for 1 gallon per day. So that shows the economy of scale. If you build a higher capacity wastewater treatment plant like centralized, it tends to be cheaper overall. And similar apply for the operation and maintenance. So it affects the whole life cycle of the project, not only when during engineering and construction, as you can see there. So for example, the operation and maintenance, every gallon per day go out of the treatment, it's $13 spent. For small wastewater treatment plant, it only spent $2 per gallon for the big treatment plant, something like Three Oak wastewater treatment plant in our areas. So you can see that there is relationship there. So from that study, they conduct many projects in the past, and with they drop a scatter plot between the construction cost and the capacity, and then they can do the regressions, and as you can see, the relationship is not linear, it is exponential or somewhere, and the more you increase the capacity, the unit cost going down. Remember the vertical axis is the cost per gallon per day of capacity. It's going down significantly. If we have 10,000, units cost about 100 per gallon. If we have 10 million gallon per day, it on the bottom right, it only $10 also. So with that in mind, we have a relationship and it's not linear. So that one, it go to the method, it cost capacity. So from that, it will be based on project physical size like how many gallon per day, right? Project physical size or production capacity. Such as the power plant. We talk about how many megawatt the project will produce for power, electricity. And from that, because it's not linear, so the equation to determine of the cost, C, is equal to Cn, the reference, something we already talking about in the index method, times the capacity of the new facility divided by the capacity of the reference facility. As it's nonlinear, we have a exponent called m in here. And let's define C and Cn already have it defined previously here. Just define what is not provided. So Q, or in this case, it will be a capacity of the current or the new facility we want to build, current facility. If we talk about the water or wastewater treatment plant, million gallon per day. If we talk about the power plant, megawatt. Qn, that it will be the capacity of the reference facility, capacity of the reference facility. And m, the exponent, it stands for cost exponent. Or cost capacity factor. Cost capacity factor. Sometimes in the book they also use that equation with the other equation they can use, and then you can see that C equal to K QM. M is the same, but where with that same equation they can use this equation, and K just simplify from that equation Cn, the reference, divided by Qn over M. So it will be the same that, and then they will define the K instead of M for you. So that is the cost capacity estimate, and where EM, what EM about, and how much M I need to determine, and that here it shows you for in the book different project equation there. Different project have and different time of project have different cost exponent M, and this is from the textbook that we have. For example, the water treatment, the cost exponent is 0.67, and for the capacity range from 1 to 100 million gallon per day. For the wastewater treatment, it depends on the time of processing unit that we have. And you, for you, those of you that environmental engineering, you are have more expertise in this area, so that you can see different kind of process like stabilization points at the end. The M is 0.57, but if we use primary with the digestion for the large, it's 0.75, and the range for the capacity in there. So it really depends on the processing unit, time of project that we can determine. So with that in mind, that is M, and this reference also available in the exam 1 reference. So you, whatever the project refer, you can be able to determine the M and determine the cost of your project that you want to be built based on the reference project. In the next video, we will apply this cost capacity for the problem 2.